Okay, so we've been going over aromatic substitution, and so it's this table that we've been going over, and we showed you how to put on halogens and sulfur and nitrogen and carbons. And we haven't shown you a few of these, like for instance, how to put on oxygen. And so I put it up here. If you want to go ahead and take a picture of it, okay? So a long process. While you take the picture, let me explain to you. The first thing to put oxygen onto a benzene ring, that actually forms a phenol, right? So here's the product right here. And an interesting byproduct is acetone. So whenever you use acetone in the lab or fingernail polish remover or a paint solvent, this is actually where it comes from. Okay, so the first step is you take benzene and you do an electrophilic aromatic substitution with the cation of propene. Okay, and so that makes a compound called cumene. Okay, so remember on the homework there was a homework where you actually saw cumene. It was either called phenyl, 2-phenyl propane or isopropylbenzene, right? Okay, now if you take that and you treat it with oxygen, okay, oxygen is actually a diradical. You can actually abstract the hydrogen from this position right here, okay? That position is called benzylic. Whenever it's next to a benzene ring, it's called benzylic. Okay, and what that forms is a benzylic radical. So here's the benzylic radical right here, okay? And that benzylic radical can then go ahead and react with the product of the abstraction of the hydrogen with oxygen. And what that forms altogether right here is this peroxide. Then what you can do is you can do a rearrangement, okay, by protonating this oxygen here at the end. Okay, you get here. And as you're breaking the peroxide bond, you're making an O plus transition state. People don't think you really make the O plus there. Okay, but that step right there is actually the electrophilic aromatic substitution right here. Okay, because you're using electron deficient oxygen to connect to benzene, and so the mechanism is addition followed by elimination leads to substitution. Right? Okay, so you see right here. Okay, here's the addition step. And lo and behold, the intermediate from that rearrangement is actually an epoxide. And then that's the addition, and then the elimination is to reform the benzene ring. Okay, and you make that cation right there. Now with that cation, if you join it with water, you make something called a hemiketal. Okay, remember from first semester? And I went ahead and I removed the hydrogen, the extra hydrogen from the water, and I put it on the oxygen that's on the benzene ring. And finally, if you go ahead and eliminate proton from the hemiketal, that's how you form this double bond right here to make acetone right there, okay? So anyway, so that's a long process to doing this, but it's a very important industrial process because people want to make phenol. Phenol's an antiseptic, and it's also used for making lots of plastics, really hard plastics. And acetone, of course, is very important here, okay? Okay, so let me show you another electrophilic aromatic substitution can be used using phenol, okay? So now most of these we've done already with no group on the benzene ring, but if we have phenol, okay, we can treat this with base, like with sodium hydroxide. And people call this phenoxide. Okay, and this, okay, let's see. I'm going to change my mind of how I draw the double bonds in here. Remember, they're fiction anyway, so they're just accounting, right? Okay, for this, you can draw another resonance structure, basically showing the electron density. You know, remember the windshield wiper, right? You can alternate the double bond and the charge right there, right? Okay. So there's the alternate resonance structure of this thing. And so if you draw that picture, okay, then you can go ahead and react that with carbon dioxide. Okay, and if you do that, Okay, you can use this picture, but let me just use the carbon dioxide here just to show you that in some sense this is a paracyclic reaction, but it also helps explain why this carbon dioxide is going to react ortho. Okay, so I'm going to go ahead and take these electrons right here, and rather than depositing on the carbon, I'm going to go ahead and make a bond here and break this bond right here. So this part right here is technically an electrophilic aromatic substitution, even though the system was electron rich. This is the addition product right here. And this is why the carbon dioxide reacts up here, because the product also has a negative charge, or the oxygen on the carbon dioxide that you open up right there, the carbonyl, it has a negative charge right there. So that's also attracted to the same sodium right there, right? So that makes everything come together nicely this way. So after electrophilic aromatic addition, then you go ahead and do what? On these mechanisms, electrophilic aromatic substitution is what? Addition followed by elimination right there, right? Okay. So we'll go ahead and eliminate this hydrogen here. We have enough base to pick up that hydrogen. Okay, and when we do this, initially, whoops, I'm getting ahead of myself, right? So initially you would form this, but if you just go ahead and neutralize all of this, then we get to a very important compound. Okay. So does anybody recognize this compound? What is this one? You guys used it in lab last semester? No? Okay. This is called salicylic acid, right? And so it's the precursor to what? To aspirin right there, right? Okay, so this is the Kolbe synthesis of that, but technically it's actually electrophilic aromatic substitution. Okay? Okay, so we've gone over all of these. I just showed you the Kolbe. I just showed you how to make a cubene hydroperoxide to do rearrangement right there. And we've done most of these, okay? Yeah, the next mechanism I want to show you how to put benzene things onto a benzene ring. Technically, you've already put a nitro group in there, and we're going to use that to actually do this diazonium salt coupling. Okay, so let's go ahead and do that. Okay, so for that, what you need to do is you need to convert the nitro group. So remember, we put on the nitro group by using what? Nitric acid and sulfuric acid, and that puts the nitro group on. And then there are tons of ways of actually reducing this to an amino group, which is an NH2 group. Okay, and so the one I'm going to give you for the exam, okay, so write this one down right there, because there is actually lots of different ways of doing this right there, is we're just going to use hydrogenation. So you guys are used to seeing, hydrogen gas and palladium, okay? Okay, so you can imagine what's happening here is, okay, now remember the benzene ring is really resilient for hydrogenation, but the nitro group is very oxidized. So you can think of, okay, let me put hydrogens on here. Okay, so I just put a hydrogen across the double bond. And then let me move the hydrogen so that I don't have a double bond here. Excuse me, so I don't have a positive charge or negative charge for that matter. So let me make this picture. And then from this one, I can go ahead and eliminate water. And I can make just an NO, okay? This one's called nitroso. Okay, this is a nitroso group, okay? An NO2. And then you can go ahead and what? Do hydrogenation again. And you really wouldn't be doing this stepwise, because remember, hydrogen is a gas right there, so you can't control this reaction. It's just going to keep on hydrogenating. Whoops, don't forget the hydrogen. And then finally, you can go ahead and you can break the oxygen-nitrogen bond, which is a lot like a peroxide, okay, by forming water. And then you'll go ahead and form your amino group. Okay? And so there's the amino group. And so there's aniline right there, right? Okay? Okay. So remember this, okay? So overall, what are we supposed to learn from here? That the nitro group can be reduced to a what? Aniline right there, right? To an amino group right there, right? Lots of steps on there. And of course, there's a lot of other reagents to do this right here, but this is the only one I'm going to burden you for the exam right there, okay? Just make sure you remember that's what that's supposed to do. Okay, now once we have that, okay, then let's go ahead and use this compound to make lots of different compounds. Okay, so for this, what we're going to do is we're going to take this compound and this is sodium nitrite. And now it's important to know about this compound because you know, the World Health Organization and different people have realized that this compound actually causes cancer. Okay, and so for instance, if you look in your prepared meats, they actually put this compound in prepared meats like bacon and hot dogs and stuff like that, right? I know you can get now you can get stuff without that on there, but it is a very common additive to especially meat. Okay, meat that has actually you know, been ground like this, right? They don't put this on steaks or things like that because that meat hasn't been ground like that, right? And the purpose why they put the sodium nitrite is because it helps prevent botulism or bacteria from growing on your food, right? Right? So the choice is die now or die later, right? Yes. Okay. But anyway, so this one causes cancer, and let me show you an intermediate actually that causes cancer. So technically, you eat it and you actually produce the carcinogen in your stomach. Because for this reaction, you need some acid and you need some heat, right? So what does your stomach has in it? Heat and acid right there, right? Okay, so technically, you're the one that's producing the. Okay, never mind. Okay. Okay, so we're gonna put some. So we're gonna go ahead and put this thing right, and we'll put some acid in there. Let's say like some HCl. So the purpose of that is actually just to protonate this thing. Okay, and we'll go ahead and protonate again. Whoops, not there, okay. We'll protonate here again. Okay, and then we'll go ahead and eliminate this. And the whole purpose was to generate this thing right here, right? Okay. And you can draw an alternative resonance structure like a triple bond between the oxygen and the nitrogen right there, right? So if NO was nitroso, what's the name of this one? Because that has a positive charge. Nitrosonium, right? Okay. Okay. So this thing is the thing that goes ahead and attaches to this nitrogen, and I'm going to go ahead and get rid of the extra hydrogen on the nitrogen just to neutralize things right there, right? Okay. So this one is a nitrosamine. And this is technically the carcinogen right there, right? So a long time ago, some Chinese scientists discovered it because there are people in China that actually ate mushroom that grows on corn, right? And the same thing in Mexico, right? And it just had a lot of this compound in there right there, and they saw that people were getting stomach cancer from eating this stuff right there, right? Okay. So anyway, so that's what we do when we eat foods with this. So once we have this, okay, let me go ahead and protonate this thing up here. And little by little, what I'm going to do is I'm going to drive out water from here and make the real intermediate that I want for these reactions. Okay, so I'm gonna protonate up there. I'm going to get rid of a hydrogen over here. Just trying to save some time here, right? And then finally, I'll go ahead and I'll go ahead and protonate here. And I'll go ahead and eliminate water. And this is the intermediate that I want. Okay? And the counterion is, I guess, the counterion of whatever acid you put in there. So on the homework, when you ask to do this, make sure you put in the counterion like chloride. Okay? So on the homework, if it says aniline and sodium nitrite and HCl, then you're supposed to draw what? The salt. Okay? This is the diazonium salt, it's called. Okay? Di for 2, azo for the nitrogens, like the sky is blue, right? Because there's not lots of nitrogen in there, right? And then because there's a positive charge, right? Okay, now this compound is our gateway to making lots and lots of different compounds. So for instance, if you want to put in carbon, okay, you could go ahead and add carbon cyanide, okay? If you wanted to put in oxygen, you could put in copper hydroxide. If you wanted to put in fluorine, you could put sodium tetrafluoroborate. Okay, that's a negative charge on the boron right here, right? If you wanted to put in a halogen right here, besides the fluorine right there, you could put in either copper chloride or copper bromide. Okay, and in all of these right there, there wouldn't be much guesswork right there. Now, there's another one I want you to learn about also right there. This compound right here is called hypophosphoric acid. Okay, hypo. Okay, it's like you've heard of hypoglycemia. Is that too much sugar or too little sugar? Okay, so in this one right here, that hypophosphoric acid right there is actually a reducing agent. Okay, because phosphoric acid usually has what 4 oxygens on it right there, right? So this is a reducing agent. Okay, so what did this reagent do with any one of those reagents, right? I mean, with any what does the diazonium do with any of these reagents? Well, you just go ahead and replace. So with the hypophosphoric acid, right? That would just make benzene again, right? Now, right now it looks a little ridiculous to convert this because we went through the whole process of doing that, but we're going to use that pretty soon. And of course, with the copper cyanide, you would put in what? Cyanide. In the copper hydroxide, you would put in hydroxide. And with the sodium tetrafluoroborate, you would make, okay, fluorobenzene. Okay, in the copper chloride, you would make chlorobenzene. Okay. Let's see, I think on the chart there's another one, like if you just put in hydrogen iodide, okay, you'll go ahead and make iodobenzene. Okay? So it seems to be a very nice reagent to go ahead and put a bunch of different things on benzene, right? But you do have to start with the diazonium. Oh, and the other thing, you have to keep this diazonium cold because the diazonium can actually react with the aniline, okay, if you actually let this thing warm up. So you got to keep this basically close to freezing or close to 0 degrees. Otherwise, it won't do these reactions. It'll react with itself right there, essentially. Okay. Okay. Now, so what is going on with these reagents right here, right? And the answer is, well, people think that different things are going on here. Okay. So let me show you. Let me show you a few of these. Okay. One, I'm going to show you this one. Okay, because that looks different than the others right there. And then I'll show you one of the copper ones to show you why that's suspiciously a little different right there, okay? So let's do the tetrafluoroborate one. Okay, so we have our diazonium. Okay, and we have its counterion. But when we mix this thing with sodium tetrafluoroborate, you can essentially think of that you're forming a new salt. Okay, here's a negative charge right here. What happened with the other salt? Well, let's see. If you had sodium and you have chloride, those are just going to be hanging around over here, right? Okay, those are the counterions that were there before, right? Okay. So people mix this, and then this one they actually do heat. Okay. So for this one and only this one, people think that what's happening is essentially you're doing an SN1 substitution. So remember what happened in SN1 substitution? You did what? You removed the what? Starts with an L? No? Okay, leaving group, right? Okay. So you remove the leaving group and you form a carbocation intermediate. Okay, so here's the carbocation intermediate. And once you have that carbocation intermediate, the tetrafluoroborate right there is basically just a source for fluoride. Okay, so that one's pretty simple. Okay, so the mechanism of that one is what? SN1 substitution right there. Okay, now the other ones with copper, people think there's something different going on because all the ones with copper can actually be done at pretty low temperatures. The 0 degrees that I was telling you, okay? And all of these are very fizzy reactions. As soon as you add the reagents, at least the ones with the copper right there, they start fizzing the nitrogen that's actually being evolved by doing this reaction. Okay, so let me show you a copper one. So I'm going to go ahead and let me be generic here. I'm going to put a group. Okay, G for group right there, right? So remember, it could be what? Hydroxide, cyanide, chloride, bromide, you know, all of these suspiciously are using this copper. Okay, now this is actually copper 1 because it only has one thing that's more electronegative than copper, right? But I'm going to put some dots on here just so that we know that copper has lots of dots in it. I'm just going to draw 2 of them, okay, just to get the mechanism across. So the first thing that people think that happens is that this is really a radical reaction. That what we do is we transfer an electron from the copper so that the copper can become copper 2, okay, which is very common. Okay. Have you guys used copper 2 in the lab yet? Have you guys reduced or oxidized benzoin to benzyl yet, or is that not okay? Oh, I'm telling you, shh, don't tell anybody, right? You're going to do that, okay? So you're going to notice copper can change colors right there, okay? Okay, so we're going to put an extra electron here, and then what happens if you add an extra electron to a pi bond? What happens to the pi bond? Sticks together, or what does it do? Okay, you can do what to it? You can break it, right? Okay, so I'm going to break one of the pi bonds right here, right? And I'm going to put 2 electrons on one side, and I'm going to put 1 electron on the other side. Okay, so I've broken the pi bond right there, right? I'm not violating anybody's, the Lewis octet rule, right? And all the nitrogens are actually neutral, right? Because adding an extra electron to a positive charge should actually neutralize things. Okay, once I have this, then I can go ahead and reform the pi bond. Okay, and that's where the nitrogen gas is going to come in. Okay, and of course, what happened to this part right here is that this became what? Copper plus, and we have our group over here, right? Whoops, I said I was going to put group, right? Okay, and now we'll form a carbon that doesn't have a hydrogen on it. It just has a radical charge on there, right? Okay, and then I can go ahead and take that radical and I can match it up with this radical, and then I can give back the electrons to the copper there. Okay, so the group becomes bonded to the benzene, which was the goal of this thing right here, right? And then if you think about it, what happened was that the copper actually now doesn't have any ligands on it, but it's now listed as copper 1. And you could stick something on there like hydroxide or chloride or bromide right there and repeat the process of doing this reaction, okay? Okay, so this copper actually can be catalytic for this whole reaction right here, okay? Okay, so that explains how we get all these groups on here. Okay, and so that's a wonderful reaction to know about right there, that if you see copper something right there, right, in a diazonium, all you have to do is reduce it off. Okay, so let's see. So I've shown you pretty much everything here. Okay, and I just want to show you 2 more mechanisms and then we'll be done. Okay, these will be, well, almost done. Okay, okay, at least for tonight's homework. Okay, so I want to show you nucleophilic aromatic substitution and benzyne substitution. Okay, now for nucleophilic aromatic substitution, it's the opposite of what we've been showing you in terms of electrophilic aromatic substitution. And in fact, it's suspicious that to be able to accomplish this reaction, you need to have what we call a withdrawing group. Okay, so what are we going to call this thing? Withdrawing. Okay, usually something with a positive charge or something that's pulling electron density away from the benzene ring. We need to have a withdrawing group on here, and then we can have like a halogen on here to be able to accomplish this reaction. So I'm going to take this, I'm going to go ahead and react this with hydroxide. And so what people think in this case is that the benzene ring is electron deficient because it has both the nitro group and it has this halogen pulling electron density away from it. Okay? You can see this dipole right here, or you can even draw resonance structures showing that this benzene ring is more electron deficient than just a regular benzene ring. So what you can do here is you can go ahead and do addition. And so I'm going to go ahead and connect that oxygen to the chlorine, to the carbon where the chlorine is. And I'm going to push this electron density all the way over to this nitro group, which explains why you need the nitro group on there. Okay, so this is the addition part. Okay, and so after addition, then now we're going to do elimination, right? Okay, so which is a better leaving group, the chloride or hydroxide? Chloride right there, right? Because HCl is a stronger acid than water, right? And so therefore it has a weaker hydrogen chlorine bond. It also has a weaker carbon chlorine bond, okay? Okay, so now we can go ahead and reverse the process. And when we do that, then we reform the benzene ring the way we had it before. And we've gone ahead and done substitution. But of course, in this fashion right there, right, you have to have withdrawing groups to be able to accomplish this here, okay? Okay, so that's the only example of nucleophilic aromatic substitution that I want you to know. Okay, and so now we want to show you benzyne substitution. What does the benzyne, okay, what does the benzyne with a Y imply? You see a Y and E, what does that imply? A triple bond, right? Okay, so we're going to form a benzene ring with a triple bond character in it. Okay. Okay, so this is how we're going to form a triple bond on benzene. Okay, we're going to put a halogen here again. Okay, let's say put something like bromine. And we're going to use a very strong base. Okay, something like sodium amide. Okay, in this case, the nitrogen is negatively charged right here. So a very strong base has a high pKa. So what people think happens right there is that you can actually deprotonate. And when you deprotonate, you can induce elimination and form something that actually has triple bond character to it. Okay, and so this is the benzyne right there. Now, of course, this thing can go ahead and react again. And so we can take some more of that amide right there, negatively charged species right here, and we can go ahead and do addition. And then when you work this up, that would explain how you would get aniline out of this reaction. Okay, now you may be wondering, well, what proof is there that you actually did this kind of reaction? And so people have done a lot of work to try to figure this out. And one of them is, for instance, labeling. Okay, you can actually like isotopically label the carbons on this benzene. So where that little star is, pretend it's actually carbon 13. Okay, carbon 13. The most abundant form of carbon is 12, right? Okay. So we put a carbon 13 in there, right? okay, then let's see. If we follow the mechanism, we would get to here, right? And the thing is that in this case, I went ahead and added the nitrogen again to where the label was. But if we did form a benzyne, there's nothing to stop the nitrogen to where the label is right there, right? But there's nothing to stop the nitrogen from reacting to the other carbon if there is really a triple bond character to this, right? Okay. So if there is a triple bond in there, people say, well, not only should you get some of this, but you should also get some of this right there, right? Okay. In other words, that the label should get scrambled, right? It will, if there really is a triple bond in there right there, right? Okay. Okay. So that's one of the proofs. Okay. But the other proof is you can go ahead and, so let me give you this as an extra credit question right here. Okay, let's go ahead and take benzyne. And react it with this. And make what? Okay, so what kind of reaction are we trying to do this if there is a triple bond character in there, right? And we want to form a benzene ring again, right? Because we want to make a stable aromatic molecule, right? Okay. But what kind of reaction are we trying to do here? Maybe we recognize it. You've seen it before, right? We covered it in chapter 16. No. Starts with a D. The Diels-Alder. Okay. So go ahead and do the Diels-Alder here, right here. Okay. Let me open up the question for you. Now, technically, there's going to be how many cyclic pi electrons? And the answer is it's not really 6, but they're not conjugated, so that's another thing about it right there. Okay, they're really 2 isolated. It's really 6 and 2. Okay, that you'll end up with. Okay. So when you're asked a special question, what should you really answer? What's 6 plus 2? 8. Okay. And that looks like a bad Huckel number, but it's not bad because what? They're isolated from each other, right? They're not. We're not really talking about that, right? Okay, so take benzyne and do a Diels-Alder reaction. This is a 2 plus 4 addition. Make sure there's a benzene ring in there at the end, right? Okay, and make sure that there's 8 cyclic pi electrons, even though they're isolated from each other, right? Will it be monocyclic, dicyclic, tricyclic, tetracyclic? Can you think about it? Okay, so we've gone over a lot of recipes, mostly to put one thing onto benzene. Okay, so now we want to learn how to put two things onto benzene. So let me show you the general pattern of the thing. Now remember when we covered the Diels-Alder reaction that we used the star method to predict where things would go? We're going to do the same thing here, okay? Okay, now this D is for not for deuterium, it's for donor. Okay, something that can donate electrons. So most of these donors that we're going to see are going to be something that has a dot on there, two dots on there. Okay, these donors right here, basically, if I put a star and then no star, star, no star, 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 okay, then basically we end up with a star at the ortho. Remember, these are the what? Ortho and the para position. Okay. So if we were doing electrophilic aromatic substitution, then it makes sense that where would electrophile want to go? The ortho or the meta or the para? Okay. Well, at least it wants to go where the stars are, right? Because the stars represent what? Electron density. Okay. We can draw resonance structures. In fact, look in your book. They show you lots of resonance structures showing that those positions have an extra electron density on it. Okay. So what happens is that statistically, the ortho is favored. What do I mean statistically it's favored over para? Because how many ortho positions are there? 2, right? So the odds are that you'll substitute ortho. But as soon as you add any little extra steric hindrance, then which position becomes more favorable? Which position? Para. Okay, para right there, okay? Okay. Now, I want to point that out because all of this is summarized on table 18. This is table 18.2, page 26 of the file right there, page 936 of the whole book right here, right? Okay. Now, notice this table is pretty long right here, right? And it looks pretty scary, right? Yes? Doesn't that look scary, right? Like lots of things to memorize. Except that, look at the pattern. What they're saying is, if this is the thing that's stuck onto benzene, then it's a what? Ortho-para director, right? Because it has what? Dots on it, right? Okay. How about all of these right here? It looks like extra stuff on here. The important thing is what is connected to the benzene ring directly, right? Those are dots also. Yes? So what kind of group is that? That's an ortho-para director, right? Okay. We saw alkyl groups were also ortho-para directors. Why was that? Because remember, they form a stable carbocation, tertiary carbocation intermediate. Okay? So you just have to remember alkyl groups are also what? Ortho-para directors. Okay? How about halogens? Do those have dots on them? Like fluorine, chlorine, bromine, iodine? They do. So what are they? They're ortho-para directors right there, right? Okay? So even though the table is long, there's nothing to memorize besides the fact that the thing has dots on there, right? If it has dots, then it's a what? Ortho-para director, right? Okay? And so if the group is small, okay, if the groups, both the donor, okay, if this and this are small, then what would be the predominant product? Right? But if there's any steric hindrance, what's the predominant product? Which one? The para right there, okay? Okay, so that's easy to predict right there, right? Okay, now what if they're not donors? What if they're like a carbonyl or a nitro group or something like that, okay? So for that, I'm going to put a W here. W is going to be for withdrawing. Okay, something that does not have a dot and actually is electron deficient. Okay, so something you can definitely see either a partial positive charge or a positive charge on there, okay? So in that case, again, you can put a star on here. Okay, but in this case, the stars mean electron deficiency. Okay. So if you were an electrophile, would you want to go to the star positions in that case? Is positive attracted to positive? No, it isn't right there, right? So if you're an electrophile and you see those star positions, in this case right there, you want to avoid the ortho-para positions. So where should you substitute? What position? Meta. Okay, meta, because meta will avoid the electron density. Okay, the electron positive regions right here, right? Okay, so if you have a withdrawing group right there, then the pattern that people observe is that these are what? Meta directors. Okay, meta directors on there, right? Okay, so now let's take a look at the table right there. Again, it looks scary because it's long. But see, why is this a meta director? If you have a carbonyl, that carbon doesn't have any lone pairs on it, right? And the carbon is electron deficient, right? Right? That means that what? Oxygen is more electronegative than carbon right there, right? So that carbon is electron deficient. Look at the rest of the table right there. What happens? Okay? All the carbonyl compounds are what? Electron deficient there, 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 there. Why is this one electron deficient? Because nitrogen is more electronegative than carbon, right? Okay. Definitely remember we've shown resonance structures of sulfur with positive charge on there, right? Right? That's extremely electron deficient. Why is this one electron deficient? Fluorine is a lot more electronegative than carbon right there, right? And finally, the nitro group. Remember the nitro group? You know, we've drawn the nitro group out for you guys a few times right there. What does the nitro group have on it, on the nitrogen? Has a positive charge right there, right? Okay. Right? Which is different than this. This nitrogen up here has a what? Has a lone pair on it. The nitrogen on the nitro group does not have a lone pair of it. It's positively charged right there, right? Okay? Okay, so pretty much we can predict then, right? The withdrawing groups will lead to what? To meta direction right here, right? Okay, so this is pretty neat because now then you can sort of predict where things should go, right? Okay, so let's say I put in, let's go ahead and do some reactions here, okay? Well, let's do it by the Friedel-Crafts alkylation. Okay, so if I go ahead and do this, and I use aluminum trichloride, okay, what should happen here? I should be able to go ahead and remove the chlorine, make a cation, and then I remember, okay, all I have to do with cations is put them onto benzene, right? Okay. Okay, now, it doesn't have a dot on it, but I should remember that this is an ortho-para. Now remember, ortho-para go together, right? Okay, so it's not ortho or para. First you have to decide ortho-para versus meta. Okay, that's what the table is divided on here, right? Okay, so is that an ortho-para or a meta director? It doesn't have dots on it, but it's not electron deficient. Okay, so what is it? Okay, that's the only one. All the others, if you see a dot, right, you know that's an electron donating group right there, right? Okay, so what is that again? These are what? Ortho-para directors right there, right? Ortho-para directors right there, right? In fact, the other day I showed you that, okay? Okay, so if that's the case right there, okay, now let's go ahead and do bromination. This was a recipe for doing bromination. Okay, so where should the bromine go? So you know it's an ortho-para director, right? So you say, well, it either go on the ortho position or the para position, right? So the question is anything here sterically hindered? Like maybe an isopropyl group that can do this, right? And so in that case, what would you predict? Okay, it should go para right there. So the major product here should be this one. Okay, because of steric hindrance right there, right? Okay, let's change over to something else right there, right? Okay, let's show you this one generically. Related to Friedel-Crafts, the previous one was Friedel-Crafts alkylation, followed by bromination. This one is Friedel-Crafts acylation. So this is aluminum trichloride, right? Remember, it gets rid of this, makes a C+, right? So you make this first, right? Okay, now if I were going to react this, let's see, let's change it up here and let's put a nitro group here. So what's the recipe for nitro? This is it right here, right? Okay. Okay, what kind of director is this carbonyl? Is it an orthopara or a meta-director? Does it have dots? Does it have dots on the thing directly connected to the benzene ring? It doesn't right there, right? Is it electron rich or electron deficient? Deficient right there. So what kind of director is it? Orthopara or meta? It's a meta director, right? Okay. So that means I should put the nitro group over to here. Okay. But let's change things up a little bit. Okay, let's take this thing. And then now let me go ahead and do, just to show you the difference here, right? Okay. Let me go ahead and do, see, the other day we talked about this reaction. It was one of the carbonyl reductions, right? We made a thiol compound, thiol acetal. And then we treated it with Raney nickel. Very similar to what? Hydrogen gas and palladium, right? Okay, so in that case, we're able to reduce this to a carbonyl. Excuse me, not a carbonyl. The carbonyl all the way down to ethylene. Or methylene, sorry. In this case, it'll also reduce the nitro group, okay? And we can get to this. Okay? And so we've got what? Two groups, what? Being meta to each other right there, right? Okay, now let's change it up a little bit right here. Let's go ahead and do another type of reaction. Okay, the other day we talked about this one using hydrazine and then base and a high boiling solvent right there. This was called the Wolff-Kishner. Okay, so review the, well, not that, okay? Let's take it from here. Here we'll do the Wolff-Kishner. Okay, so this stuff is just a review right here, okay? Okay, so I'll do the Wolff-Kishner. And that'll go ahead and reduce the carbonyl down. Okay, now if I add a nitro group. Where should the nitro group go? Okay, assume R is a long chain. Okay, not just a hydrogen right there, right? So where should it go? What kind of group is an alkyl group? An orthopara or a meta-director? What is it? Okay, how many people vote orthopara? How many people vote meta? Okay, it's orthopara. Okay, in this case right here, again, I would predict that this should go over here. And then remember the one I told you that we would use right there is some kind of hydrogenation, right? And so therefore you can go ahead and make this right here, right? Okay. So basically by, controlling the steps of reduction right here, you can get to two isomers that basically have a different what? Different connectivity to it, right? Okay. Now, so I've shown you how to make the para one. We use steric hindrance to get to the para one. I've showed you how to make the meta one. Does anybody want to learn how to make the ortho one? Okay, what if you had your heart set on ortho, right? Okay, so let me show you the ortho one. Okay, because study this one again. Okay, let's go through it one more time right there, just to show you that we can control things right here, right? Okay, so I did Friedel-Crafts acylation, right? Something we covered the other day right there, right? Okay. In one case, I proceeded to use the carbonyl as a meta-director, right? I kept the carbonyl right there, and then I went ahead and reduced the carbonyl by using one of the three methods So I went down this road right here, right? Okay, and that's how I got to this compound on the lower right-hand side. Okay. In the other method, I took the carbonyl compound and I went ahead and reduced it to convert it over to an orthopara director. That's the left route. Okay. Okay, and then I introduced the nitro group using nitric acid and sulfuric acid right here, right? Okay, and then I went ahead and reduced the nitro group down to an amino group right there, right? Okay. Now what's really neat is I can take this amino group now and I can use the diazonium and I can convert it to whatever I want. Remember what I showed you today, using copper this, copper that right there, right? Okay. So you can basically mask the fact that there was even a nitrogen in this compound eventually. Okay. Okay. So now let me show you the route to making ortho compounds. Right. So let's start one more time right here. Okay. Now, why am I using this Friedel-Crafts acylation? Because that's the only way of getting linear chains onto the benzene ring, right? Otherwise, you get rearrangements. Remember we discussed that? So this is just repetition. Okay, so we got this right here, right? Okay, let's see. There was another way of reducing things. That was, let's see, acid and a metal zinc. That was the Wolff-Kishner. Okay, so you can get to that. Okay, now what I want to do is I actually want to block the para position so that I can actually force things to go to the ortho position. Okay. Now, the other day we talked about this reaction. The fact that if you take a sulfuric acid, dehydrate it, you can make sulfur trioxide, and sulfur trioxide will make that benzene sulfonic acid. Okay. Now, technically, the byproduct of that reaction is the water that you took off from the sulfuric acid. Okay. So it turns out that this reaction is very reversible. Okay. If you add the fuming sulfuric acid, you'll make the benzene sulfonic acid, right? Okay. What do you need to add to remove the benzene sulfonic acid? If it's a reversible reaction, how do you use Le Chatelier's principle to push the reaction to go back to benzene? What would you add? Something cheap. Something easy. What would you add? Did somebody say it? Water. Water, okay? So you can put a sulfonyl group in, right? By adding sulfuric acid. And then you can go ahead and remove it by adding water, right? And a little bit of heat, and it'll go backwards and you can remove it. Okay? Okay, so we're going to use that. Okay, so we're at to this stage right here, right? So what kind of director is this? This is an orthopara or a meta director? It's not a new question, right? Just asked it a few minutes ago. What is it? Orthopara director, right? So now I'm going to put in the fuming sulfuric acid. Where is it going to go? Okay. Okay, and then now I can go ahead and put the nitro group in there. Okay, now notice this one. Okay, this is very important because this is the first time I'm showing you putting three things on benzene. Okay, so watch this. Okay, very very important concept. Okay, it's called voting. Okay, or I call it voting. Okay, where does the alkyl group want things to go? Okay, this thing. Where does this thing want things to go? What kind of director is this? It's a what? We just said it. It was a what? Orthopara director, right? The para position to it is blocked. So that means this is where it wants things to go, right? Okay. Okay, but now the question is the sulfonyl group. What kind of director is it? Is it an orthopara or a meta director? It's a meta director. So what are the groups meta to that sulfonyl group? Okay. Are they the groups ortho to it or are they the groups meta to it? It's the groups meta to it, right? Okay, so where are the groups meta to it? Or the positions meta to it? It's the same place, right? So both of these groups voted right there, and when they voted, what happens? they both decide, yeah, that's a good place for them to go right there, right? Okay? Okay? Okay, so now we'll put the nitro group over here. Okay, what do I need to add to get rid of the sulfonyl group? What was the magic recipe to make it go backwards? Water. Okay, so we'll put in water. Okay, and then I can go ahead and use my palladium and hydrogen gas, or palladium and nickel, right? There's a bunch of different ways of doing this, but... And I can actually get this to what? To go ortho, right? And then I can take the amino group and I can react it with the stuff in the bologna, the sodium nitrite, right? Make a diazonium and then replace it with whatever I want, right? A chlorine, a bromine, a cyanide, or whatever, right? Okay, right? Okay, so 3 very nice strategies right there, right? Okay, so let's study this again right there, okay? Let's make sure we understand this right there, okay? Okay, if we want things to go meta right there, right? Should we reduce the carbonyl or not reduce the carbonyl before we add the group? Should we reduce it or not reduce it? How many people say that we should reduce it if we want it to go meta? Okay, okay, no, if we wanted to go meta, we should leave the carbonyl like it is and let it do its job of directing things what? Meta, right? Okay, now if we want things to go para, we shouldn't keep the carbonyl, we should get rid of it. Right, and that's what we did over here. Right, we got rid of the carbonyl, right? Converted it into an orthopara director, the group there. Made things go what? Para, which is the most common thing unless the group is very tiny. You know, what did I talk about tiny? Like this was a methyl, right? Rather than, if this was a methyl, right? Then you should worry about making ortho products right there, right? Okay. Okay, but if it's large right there, right, then you'll go para, right? And then you can go ahead and reduce that and nobody will know, okay? Okay, one last thing I want to, well, actually a few things right here, right? Now, if there's a bunch of ortho at the top of this table, orthopara directors, and there's meta at the bottom of the table, what's these classifications here on the left side where it says very strongly activated, activated, then it says deactivated. It actually has here hydrogen as a reference, then strongly deactivated right there, right? Okay. This is the other reason why things go where they go. And if we use a voting scheme right there, this is why things follow the thing, okay? The very strongly activated means that it's just the dots. The dots are only for you, okay, for doing the electrophilic aromatic substitution. These are very fast reactions. In fact, it's talking about the rate of the reaction, okay? So this is the fastest ones right there, okay? Okay? But in this case right here, these over here, by putting stuff on here or by locking up the hydrogen with an alkyl group, right? Remember how this had a hydrogen on there, right? All of a sudden, these groups are not as donating as before. Okay, in fact, these groups are not as fast for doing electrophilic aromatic substitution. Now, of course, if you don't have dots, then you're not as donating as something that has dots. Okay, this is benzene. So that means that, remember the other day we were talking about over-alkylation, right? That when if we took benzene and we try to do this reaction, we might end up with what? This, because the product, right, is actually more reactive than benzene, right? Okay, that's this. This is what this is telling you, right? That the product is more reactive than benzene. Okay, now when you get to the halogens, okay, remember halogens are electronegative, so they are pulling electron density away from the benzene, and that's why you don't have to worry about, you know, if you take this and you react with bromine and aluminum trichloride, you don't have to worry about making, putting 2 bromines on here, okay, that easily right there, because what? Because that thing on the right side doesn't react as fast as the thing on the left side. So the bromine will always come back over to here first before it comes over here. That's what deactivating means, okay? The reactions are slower. Now, of course, if you start you don't put any dots on there and you put withdrawing groups right there, then things get slower and slower to the point that a nitro group makes the reactions go very, very slow, okay? Okay, so let me show you a voting example here that might be of interest to you, okay? Okay. Okay, the methyl group, ortho para or meta director? It's an ortho para director, okay? Okay, now this is an example of a small group. So statistically, I think your favorite, in fact, I think I had some students do this once and they got like a 66% yield of ortho and a 33% yield of para. Okay? But now, let's do some voting here, okay? These are the start positions for the methyl group. Okay, very nicely. The start positions, well, what kind of director is the methyl group? The methyl group is a what? Ortho para director. That's its ortho para positions. Okay, the nitro group is also a what? Well, now it's a meta director, right? It's got a positive charge on there, right? Very nicely, the nitro group also votes to put things in the same position because the nitro group is a meta director and those are the meta positions. Okay. Okay, now we can repeat the nitration. Okay, and statistically, one side is not favored over the other. So let me go ahead and put let me put this over here. Okay. Okay, so the methyl continues to want to put things either ortho para, but the para is now blocked. Okay, and the nitro groups want things to be meta to them. So very nicely, all 3 groups in this case vote to put the next group on the same position. Okay? Okay, so the question is, what is this compound called? Okay, have you guys ever heard of TNT? Right? So this is what? Trinitro what? Toluene right there, right? So very funny, I actually wanted students to make the para product, or the first para product right there, right? Okay. Fortunately, we did not make TNT because it takes a lot of work to make the TNT, right? Why? Because every nitro group, what did it do to the reaction? Every nitro group I put in there made the reaction go what? Slower and slower, right? So fortunately, what we actually isolated from the reaction, because we didn't run it, we only ran it for a half an hour, was this compound. Okay? And we isolated this one right here because basically this was a solid and this was a liquid. Okay, so this one went through the filter and this one is the one that we were able to isolate right there, right? Okay? Why? Because the first reaction is the fastest one because there's no nitro group on there, right? But every time you put a new nitro group on there, the reaction gets what? Slower, slower, and slower. And that's why we didn't blow up, when we were making this stuff in the lab, right? Okay, right? You would have to actually work a little harder or keep the reaction going longer before you could make your own what do you call it, explosive, right? Okay, should we stop the question? What question? Okay, so please study those examples. How do I get something to be ortho? How do I get something to be what? Meta? How do I get something to be what? Para? Okay? Right? How do I make isomers of the same kind of things right there, right? The other thing too, okay? There is a bunch of homeworks right here, right? Technically, when exam 2 is next Tuesday, right? Yes? So let's see. So tonight you're doing aromatic helicycles, then you're doing benzene synthesis. So reviewing what we've been talking about putting one thing onto benzene on Thursday, right there. Okay. But for the next exam right there, you should try to do as many of these as you can. Okay. Because they're just practices of what we've been talking about today. Okay. In other words, how does one thing go on there, and how does the first thing decide how the second thing goes on there, right? Okay. So some of these are interesting. I mean, if you want to skip some of these, but do them ahead right there. Acetaminophen, how would I use what we've been talking about to make what? Tylenol, ibuprofen, how would I use the technology we talked about today to make, ibuprofen, that kind of stuff right there, right? Okay. So all of these have examples of putting more than one thing onto benzene rings, okay? Okay, how are you guys doing on the question? You guys almost finished? Should we stop it now? Ooh, 99. Should we get to 100 or stop it? Or I'll stop it at 36 minutes. Okay. Okay, so what we wanted to do is connect that to that, and make that go over there, right? Okay, so how you put the double bonds in there didn't really matter. Okay, but you should have made something like this, right? Okay. That's the Diels-Alder. Okay. So you could put the double bonds this way or the other way. They're both counted the same right there, right? Okay. Okay. I'm just curious what other people did. Well, they were missing carbons, right? Okay. Okay, never mind. Okay, you're missing some carbons, right? You're missing 2 carbons right there, right? Let's see what happened over here. Okay. I guess you were trying to do a 2 plus 2? Okay, but no, a Diels-Alder is a 4 plus 2, right? Okay, Dax? Dax here? Okay. Okay, let's see. Let me give you a problem here. Let's practice some of this right now. Okay, so what is G? So write down the question. This is the first thing I'm going to ask you to draw on Thursday. Okay, write down the question. Right? But in the meanwhile, right there, I'm going to ask for some volunteers to come up here and help us through some of these. Okay, just to see if anybody was awake this morning. Okay, everybody copy the question down, right? Okay, so can anybody come up here and give us A? Anybody who's been through the class, that's been in the class, you know, for the last week and a half or so. Right there, okay? Can anybody give us what A is? You can show me on a piece of paper you want, you know, and then I'll tell you yes or no, and then if you're right, then. No, this they actually won't have the point.
Is it just the party thing then?
Not quite. So there's something else we have to review. Look at the okay. It's Anna, right? Yeah, just right there. Okay, everybody agree with Anna? So remember, Friedel-Crafts alkylation, they're subject to what? Rearrangements of primary alkyl groups, right? Okay? Okay, well anyway, I agree with Anna. Let's give Anna a hand. Okay, okay, anybody want to come up here and draw B? Anybody know what happens with B? Yeah, you guys are all tough on your chair, right? You know, but when I asked you to come up here, bunch of chickens, huh? You guys are going to say, "Oh, Dr. Salvador's a bully," right? No, but anyway, come on, somebody. We even reviewed this reaction today. Come on, you guys, somebody. Okay, show it to me, and then I'll. Alkyl groups are ortho, para, or meta directors. Okay, let's give Aaron a hand. They're ortho-para directors, right? Yes? Okay. And in this case, I would surmise that it should go para, right? Because of steric hindrance, right? Okay, anybody going to come up here and draw C? Show it to me if you're not sure. I'll tell you yes or no, right? Go right down here. Now remember, these two groups are on there. One of them is an ortho-para director, and one of them is a meta director, right? Yes. And in this case, both of them are voting in for the same position, right? Okay. Okay. So Bianca put the nitro group ortho to the isopropyl group, and she put it meta to the sulfonyl group, right? Because the sulfonyl group is a meta director, right? Okay. Let's give Bianca a hand. Hey, how about D? Ooh, we have a. Okay. Okay. Your name, sir?
Luis
Luis. Okay, Luis.
Salazar.
Come up here.
Anyway?
How about right now? Okay, so Luis got rid of the sulfonyl group, right? Because remember, the sulfonyl group is reversible, right? Okay, let's give Luis a hand. Okay, hydrogenation. What does hydrogenation do? Got about a minute. Let's see. Any hydrogenation. What does hydrogenation do? Okay. Yes, okay. Come on.
Oh, that's right.
Yeah.
This is E, right?
Yes, right there. This is also to prove that it's not just my handwriting, the screen is very slippery, right? Come in and try my screen right here, it's very slippery. Okay, so the nitro group gets reduced to a what? An amino group, right? Okay, let me move some stuff out of the way. Yeah, let's give Jacob a hand. Guys are so mean, no encouragement, right? Okay, so. F. What does the bologna stuff do? What does our carcinogen do for us? I just mentioned these things so you'll care, right? You know. Why do I have to take organic chemistry, right? What's it used to, right? What does sodium nitrite and some acid at 0 degrees do for you? Anybody know? Okay, anyway, time's up, and so you guys figure out the rest of it yourself right there, right? Okay. I'll ask this on Thursday. Remember, the review was also due on Thursday morning. Please try the review, okay? It always helps to look at material ahead of time before you review. Makes your questions more pointed. Makes you be able to study more. And also, you can ask questions about other exams. You can come by this week and ask about other exams also right there, right? Okay?
Was it G?